trends. So what exactly are periodic trends? Periodic trends is when you look at a periodic table, you can actually see a trend of different things going across the periodic table or a trend going down the periodic table. So what are those three trends that we'll talk about today? That's going to be your electronegativity, which is the first one, and also the atomic radius. Let me just get my pen. So there's this one, atomic radius and ionization energy. The way I try to remember this is that if you understand one thing, you can also always use logic to sort of deduce to the other, and also to the last one. So you don't really have to memorize three different trends. I would just say memorize one thing and use that to make sense out of the other ones, because once you have understood that, then you don't have to memorize it. So first thing is electronegativity. What exactly is electronegativity? So electronegativity is basically for the ability for an atom to sort of pull electrons or attract electrons to itself or to itself to make a bond. So if you have a high electronegativity value, that means it has a lot more ability to pull electrons to itself. So it's the stronger it is. One example, one diagram I think about is just, okay, if you think about yourself giving yourself a hug, if you have a high electronegativity value, that means you have a stronger hug. Just like this guy, the ability for it to pull electrons to itself to form the hug. But if you have a lower electronegativity value, that means that your hug won't be that strong. So if you were to bond with another element with a higher electronegativity value, that means that they can actually pull more of your electrons towards their side. So you actually create a dipole or an even distribution of electrons. So that's keep that in mind of what electronegativity is the ability to sort of pull an electron, attract the electron to itself to form a bond. So how do we look at this trend? One thing you need to remember is that fluorine, if you have your electronegativity table with you, fluorine is the highest one and has a value of 4. That means that fluorine is very, very strong at attracting the electrons. So because you know that fluorine is the highest, the trend is going to be going across towards fluorine. So if you are going across this this row, that means that you're increasing in electronegativity value. And since fluorine is the highest one, so then we can also say that going up towards fluorine, or just going up in general for each family, you're going to increase your electronegativity value as well. So one thing you need to know is fluorine is the highest one. That's 4.0, that's the value. And because fluorine, it's at this corner, the highest one, so then your electronegativity value will go towards fluorine, which is increases across. So these ones are all increasing across. And because it's up at the top right corner, it's also increasing up. So that's the first thing. So that's the electronegativity value. The next one is atomic radius. So atomic radius is a little bit cut off here, but this is about atomic radius. Basically, if you know about the radius of a circle, this is how large is your atom, or how large is your atom. So we're looking at the radius. How far are the electrons away from the center nucleus? So since if you think about fluorine is the highest electronegativity value, so that means that fluorine can hug itself the strongest or attract electron to itself the strongest. Well, you would think that the radius, the size of the atom would be smallest for fluorine, and that is true. So fluorine would have a really small atomic radius. So if fluorine has a really small atomic radius, that means the trend of going across towards fluorine will decrease. And then since fluorine's top right corner, that trend will be decreasing towards fluorine as well. So in all these different families, they're decreasing up. And if you look at all these individual rows, they're decreasing across. So try to make sense that electronegativity holds it to itself. So if it's really strong hold, that means that it has a very small atomic radius. That's about it. What about if we were to look at, here's a sample diagram. You can see fluorine is really, really small, so it decreases across and then also decreases up. So if you look at each of these rows, it's all decreasing across. If you look at for these families, they're all decreasing up towards the top. What about atomic radius of ions? So what this means is that if you look at, say, Cl negative and compare that to Cl, which one would have a larger or smaller atomic radius? So in order to think about this, this is your anion. So that negative means that it has gained and electron. This one is neutral, so it has the same number of protons and electrons. So if you draw up this Bohr diagram, Cl actually has more electrons than protons. And because of this one, you can see that there's electrons on the outside, electrons on the outside. I'm not going to draw the Bohr diagram, but you can see that because you have an extra electron on the outside, these electrons in the closer energy levels actually shields them. So they're like shielding effect. So they're like a little shield that shields them from the positive charge of the proton. That means that this electron can wander further away, making your atomic radius larger. Whereas in a neutral atom, you have the same number of protons and electrons, so you have an equal attraction, so your radius is not as large as if you were to have an extra electron. These electrons, because they're on the outside, they can actually repel, making the outside electron go farther away, making a larger atomic radius. What about if you have something like Na plus and just Na? So let me see if I can erase that one. Let's see, just erase all this. So just Na plus and Na, well, we have two ions right now as well. So this one, instead of having negative, this one has one less electron, and this one has the same number. So which one would be larger or smaller? Well, because you have less electron, that would be more positive than your electrons. So that means there will be more attraction, and since you have a stronger attraction, that will be smaller in radius. So try to make sense out of this with the number of electrons, and since this is the same, you would have the same sort of atomic radius. Right now we're comparing the ionic form and see how that would play a part. So next thing is the third trend. That's the ionization energy. What exactly is the ionization energy? Ionization energy is basically the energy required to remove or strip away an electron, hence making it into an ion. So if you think about it, if it's the energy to remove an electron, well, what happens if you have a very electronegative, someone that was an atom that can hold itself really strong and tightly? Well, if it's a high electronegativity value or atom, that means that it would require more energy to remove the electron, right? So that's how you would want to think about it. So in ionization energy, if you think about fluorine being the highest one, well, that's the most difficult to remove an electron. This one will have high ionization energy. And then the trend will follow as well. So it increases across and it increases up because your atom size is smaller. Smaller atoms, that means that has a tighter attraction, more difficult to remove the electron, hence higher ionization energy. So high ionization energy means difficult to remove the electron. Okay, so that's that. That's your three trends: electronegativity, atomic radius, and ionization energy, and they sort of relate to each other as long as you remember one thing, fluorine, and you can make sense out of them. So what about the ionization energy? Let's look at this one. Here's aluminum, and you have these different number of ionization energy. So the first ionization energy, second, third, and fourth. What do they mean? The first ionization energy is the first electron being removed. This one is now the second electron, and then the third one, and then the fourth one. So the question is, why is there a huge jump from 2,700 kilojoules per mole to 11,000? That's a lot of ionization energy required. So if you look at this, if you were to look at the electron configuration of aluminum, aluminum is what? 1s2, 2s2, 2p6 and 3s2 and 3p1, I believe that is correct. And if we were to focus on the valence electrons on the highest energy level, that's how we look at valence electrons, we can see this. This is my 3s2 is like this in my molecular orbital diagram. This is my 3px and then 3py and 3pz. And if we were to fill in my valence electrons, I have 3 electrons to fill in, so that's 1, that's 2, that one first, and then the third one. The first ionization energy here is easy. It's a small number. If you look back on this one, it's a small number, 577, because this electron is in the outermost orbital and it's empty, so it's easy to remove because it's not very tightly attracted. The next two electrons, if you look at this, well, it is a lot higher than 577, but you can see that the second and the third are relatively almost similar. So to remove this one requires some energy because it's in the s orbital, and this one gets a little bit harder, but because it's in the third energy level in s orbital. So now the question here is the fourth ionization energy. So that's 2px, 2py, and then 2pz. That means that it's this one. I'm just going to fill in all this. So if you look at this one, fourth ionization energy has a huge jump, and if you look at it, it makes sense because the next one is you're removing this electron out from a full orbit. So this is all, the p orbital is all full here, and that's the reason why it requires so much more energy to remove the electrons. So that's your what you call successive ionization energy. And when you are given these ionization energy diagrams, be sure to look at the trend or see where the big jump is and make sense out of where exactly are the electrons in the orbitals. If you can see that are your electrons in a full shell or an empty shell, that will tell you the difference or in the number of valence electrons. And you can see that this one has 3 valence electrons because this one, this big jump, is where you have the full orbital. So that's how you can tell. So that's your periodic trends. Hopefully has made or has cleared up any misunderstanding. And I'll see you next time. Thanks for watching.